Hello everyone. In this video, we will be discussing the part B of our internal, that is the similarity and dissimilarity in feedback. So let's get started. So here's the question. Briefly outline how to compute the similarity between student feedback profiles described by A. Nominal attributes, B. Asymmetric binary, C. Numeric attributes, D. Term frequency vectors. So here's the first A. Normal attributes. Normal attributes values are categories without order. Example, department, which is equals to, in curly braces, computer science, electrical engineering, mechanical engineering. So common approaches are simple matching, binary similarity for true profiles P and Q, for a nominal attribute S of P comma Q equals to 1 if same category, 0 if different. Dissimilarity D is equals to 1 minus S for multi-attribute nominal vectors, average or the sum of mismatch and matches. Second is one hot encoding plus numeric distance. Convert each category to binary vector one hot, then use cosine or Euclidean on those binary vectors. These are mixing with other attribute types. Third is the overlap coefficient, matching coefficient for multi-valued nominal attributes. If attribute may have multiple choices, example elective chosen, use an overlap Jaccard. J of A comma B is equals to intersection B divided by A union B. That is, the similarity is equals to 1 minus J. Next is asymmetric binary attributes. Asymmetric binary means 1 is more informative than 0. Example, attended workshop, yes, no, where yes matters more. Common metric, Jaccard coefficient, ignore 0, 0 matches. For two binary vectors P, Q, J of P, Q is equals to M of 1, 1 divided by M of 0, 1 plus M of 1, 0 plus M of 1, 1, where M1 is equals to number of attributes both have 1. M10 is equals to attributes P is equals to 1, Q is equals to 0. M01 is equals to P is equals to 0, Q is equals to 1. Dissimilarity is equals to 1 minus J. Next is numerical attributes, CGPA attendance percentage. Numerical attributes may support classical distances measured, that such as Euclidean distance, that is dE x comma y is equals to under root of summation I xi minus yi to the power 2, that is whole square. Manhattan L1 distance d1 x comma y is equals to summation of I xi minus yi. Chebyshev L infinite distance, that is maximum absolute coordinate difference. Standardization or scaling. Before computing distances, standardize Z score or scale to 0, 1. Otherwise, attributes with larger ranges dominate. Zi is equals to xi minus mu divided by sigma. Malhovis distance accounts for correlations. Dm x comma y is equals to under root of x minus y to the power t s to the power minus 1 x minus y, where s is the covariance matrix. Next is term frequency vectors. Text is typically represented as vectors. Common similarity measures cosine similarity, measures angle, ignores document length. Here's the formula for cos theta that is given here. The similarity can be 1 minus cos. Euclidean on TF IDF normalized vectors. Compute TF IDF, the normalized Euclidean distance between normalized TF IDF vectors relates to cosine. KL divergence, Shannon for probability distribution. Treat normalized TF as probability distribution and requires smoothing. Soft measures word embeddings. For semantic similarity, use average words vectors or sentences amending and the cosine. On to the next question, we have question number 6. Suppose two student faculty indirect profile are represented as tuple. Here's are the given tuple P and Q. So we have to compute Euclidean distance, Manhattan distance, Minkowski distance with h is equals to 3, supermum, Championship distance. So let's calculate all this. Step 1, we have to compute coordinate wise differences, that is delta, that is p minus q. So here we have calculated the coordinate wise distance. So on to the Euclidean distance, that is dE is equals to under root of 2 square plus 1 square plus 6 square plus 2 square, which whole gives an approximate value of 6.082039325. Okay, on to the Manhattan distance, that is d1 is equals to 2 plus 1 plus 6 plus 2, that is 11. On to the Minkowski distance with h is equals to 3. We have 2 cube plus 1 cube plus 6 cube plus 2 cube whole to the power 1 by 3. That gives an approximate value of 6.153449. onto the supermum distance, that is d infinite is equals to max of modulus of 2 comma 1 comma 6 comma 2, that gives 6. Next question, we have the median score is often a key holistic indicator. When dealing with a massive student feedback datasets, propose methods for median approximation, analyze the complexity and suggest heuristic to balance accuracy versus efficiency. Exact methods when feasible. Deterministic linear time selection, median or medians, median of medians. Worst case, O of n times. O of n extra space, good when you need exact median and you can read data multiple times or have random access. Start and pick medium, O n log n time, and O n memory and external sorting for disk. Not ideal for massive streaming data. Streaming on large scale approximate algorithms. Two heaps. Maintain a max heap for the lower half and min heap for the upper half. Each new element inserted in O log n time, median retrieved in O1. Memory O(n) if you keep all elements, but if streaming and you must keep n, memory grows. Practically you can store data. Reservoir sampling plus exact median on sample. Key sample of size k. Example k is used to develop of 4. Time O(n) to sample, O log k to sort sample. Error can be bound probabilistically with large enough k if you get tight confidence intervals. Good heuristic when you can tolerate probabilistic error. Approximate quantile algorithms, guaranteed error. Greenwald-Khana GK algorithm, deterministic, provides E approximate quantiles with space, stream friendly, mergeable. Q-digest, T-digest. Practical mergeable T-digest is excellent for extreme qualities and distribution, small memory and good accuracy for median. Complexity. Update cost typically or amortized constant memories 0, 1, E. So histogram or binding approach. Maintain fixed bins counts, approximate median by walking cumulative counts. Space equals to number of bins B, accuracy depends on bin width. Fast updates O1, good for bounded range data. Distributed map reduce approach. Compute local summaries, quantile sketches, example T-digest or partitions and merge. Mergeable algorithms like GK or T-digest are preferred. Complexity. Linear total work across nodes, low network overhead to send the digest objects. Accuracy versus efficiency heuristics. If you need exact median really and data set fit disk, use selection. For streaming or online dashboards, use T-digest or GK. Small memory, mergeable, guaranteed, error bounded. For simple engineering trade-offs, reservoir sampling plus exact median or sample yields, probabilistic guarantees. Sample size chosen via desired confidence interval. For skew distribution or extreme quantiles, T-digest performs better than histogram or GK in practice. If many groups, maintain separate digest streams per group. Memory scales with hashtag groups. Consider hierarchical summaries per batch digest, then merge. Question number 8. Given the sample dataset, two attributes faculty responsiveness A1, infrastructure support A2. Table for student S1 and S1 to S5. So we have been given a table from S1 to S5 and the student A1, A2. So what is our task? Rank existing student feedback profiles by similarity using ex-Euclidean Manhattan supermum and cosine similarity. Normalize each student's vector to unit length and recompute using Euclidean distance. Here are the common formulas that we will be using for the Euclidean distance, Manhattan distance, supermum, cosine similarity, normalization of vector. So let's calculate all this. Here is the step-by-step calculations of the difference of each student component-wise from S1 to S5. So, distances similarities, Euclidean distance dE. So here we will be calculating the Euclidean distance from S1 to S5. The distance for S1 is 0.144213562 and for the S5 is 0.6082762532 as shown in the screen. Euclidean ranking closest to farthest, that is S1, S4, S3, S5, S2. That is the order from the closest to the farthest. Now using Manhattan distance, S1 0.1 plus 0.1 that is 0.20, zero point 0.6 plus 0.3 that is 0.9, 0.2 plus 0.2 that is 0.40, 0.2 plus 0.1 that is 0.30, 0.1 plus plus zero point 0.6, that is 0.70. Manhattan ranking closest to farthest, S1, S4, S3, S5 and S2 respectively. Supremum Chebyshev. Maximum of quadrant absolute differences. S1, S2, S3, S4, S5. So the maximum values we have taken up from the given. So the supremum ranking is S1, tie S3 and S4 because they have the same values and same for the S5 and S2. So let's continue. Cosine similarity. Now we will be calculating the cosine similarity from S1 to S5. For S1 we have got an approximate value of 0.999991. For S2 we have got 0.995752. For S3 the approximate value is 0.999969. For S4 it is 0.999028. For S5 it is 0.965363. So ranking the cosine value from higher is equals to more similar. So S1, S3, S4, S2 and S5. This is the ranking we have got from the cosine similarity. On to the part B, normalize each student's vector to unit length and recompute Euclidean distance. Step 1, normalize query x. So the x norm we have got after the calculation is an approximate value, that is 0.6585046, 0.7525767. So on to the next step, normalize each SI rounded to 7 to 8 decimal places as shown. So for S1 we have got an approximate value of 0.661621, 0.749839. For S2 we have got 0.724994, 0.68879495. For S3 0.66643638, 0.74744093. For S4 we have got 0.624690, 0.78088688. For S5 we have got 0.83200503, for 0.55470002. Now, step 3. Euclid distance between normalized vectors and x norm. Compute d is equals to si to the power norm minus x norm. So, s1 norm versus x norm difference is equals to d is equals to under root of 0.003117 to the power 2 plus minus of negative of 0.00273888 to the power 2, which gives an approximate value of 0.00414935. Similarly, we will be calculating for S3, S4, S2 and S5. Then we will be ranking after normalization, Euclidean on unit vectors. So it will be S1, S3, S4, S2 and S5. So this was our part B. Hope you liked the video and watched till the end. Thank you.